The idea that matter is made up of tiny, indivisible particles has been around for centuries. Ancient Greek philosophers, notably Leucippus and Democritus, developed the concept of atomos. Atomos means uncuttable or indivisible in Greek. They believed that these fundamental particles were eternal and unchanging. Everything in the universe was thought to be composed of different arrangements of these atoms moving in a void. However, their ideas were based on philosophical reasoning rather than experimental evidence. It was not until the 19th century that the atomic theory was revisited with a scientific lens. John Dalton's atomic theory, published in the early 1800s, marked a turning point in our understanding of matter. Dalton's theory rested on two fundamental laws: the law of conservation of mass and the law of definite proportions. The law of conservation of mass states that matter cannot be created or destroyed in a chemical reaction. The law of definite proportions states that a chemical compound always contains the same elements in the same proportions by mass. For example, water, H2O, always contains hydrogen and oxygen in a ratio of 1:8 by mass. Dalton reasoned that these laws could be explained if matter was composed of discrete particles called atoms. He envisioned atoms as tiny solid spheres, like billiard balls. While his model was simple, it successfully explained many chemical phenomena. Dalton's atomic theory provided a framework for understanding chemical reactions and the behavior of gases. It also allowed chemists to determine the relative atomic masses of different elements, which was a crucial step in the development of the periodic table. Despite its successes, Dalton's theory had limitations. It could not explain why elements combined in specific ratios to form compounds, and it did not account for the existence of isotopes. In the late 19th and early 20th centuries, a series of groundbreaking discoveries revolutionized our understanding of the atom. Thomson's discovery of the electron in 1897 demonstrated that atoms were not indivisible, as Dalton had proposed. Thomson's experiments with cathode rays showed that these rays were composed of negatively charged particles, much smaller than atoms. He named these particles electrons. Thomson proposed the plum pudding model of the atom, in which negatively charged electrons were embedded in a positively charged sphere, like plums in a pudding. This model was soon challenged by Ernest Rutherford's gold foil experiment in 1911. Rutherford bombarded a thin gold foil with alpha particles, which are positively charged particles emitted by radioactive materials. To his astonishment, some of the alpha particles were deflected at large angles, and a few even bounced back towards the source. This result was unexpected based on Thomson's model, which predicted that the alpha particles would pass through the atom with only slight deflections. To explain his observations, Rutherford proposed that the atom's positive charge was concentrated in a tiny, dense nucleus at the center of the atom. Rutherford's nuclear model of the atom was a major breakthrough, but it still had some shortcomings. According to classical physics, electrons orbiting the nucleus should emit electromagnetic radiation, lose energy, and spiral into the nucleus. This would make atoms unstable, which contradicted the fact that atoms are stable. Niels Bohr, a Danish physicist, addressed this problem in 1913 by incorporating the principles of quantum mechanics into the atomic model. Bohr proposed that electrons could only occupy specific energy levels around the nucleus. These energy levels were quantized, meaning that electrons could only have certain discrete energies. When an electron jumped from a higher energy level to a lower energy level, it emitted a photon of light with energy equal to the difference in energy between the two levels. Bohr's model successfully explained the line spectra of atoms, which are the specific wavelengths of light emitted by excited atoms. However, Bohr's model had limitations. It could not accurately predict the spectra of atoms with more than one electron, and it did not fully account for the wave-like nature of electrons. In the 1920s, quantum mechanics revolutionized our understanding of the atom. Quantum mechanics is a branch of physics that describes the behavior of matter at the atomic and subatomic levels. It is based on the idea that energy, momentum, and other physical quantities are quantized, meaning that they can only take on discrete values. Quantum mechanics also introduces the concept of wave-particle duality, which states that particles, such as electrons, can exhibit both wave-like and particle-like behavior. The modern quantum mechanical model of the atom describes electrons as existing in a cloud of probability around the nucleus. These clouds are called orbitals, and they represent the regions of space where an electron is most likely to be found. Each orbital is characterized by a set of quantum numbers that describe its energy, shape, and orientation in space.
Thank you for watching Ways of Nature.